Hello everyone, I'm Mason Housenga. I'm a junior at the University of Illinois at Urbana-Champaign studying engineering physics, and I've been working at the nuclear physics lab on campus for about 2 years now. And what we're doing at the lab is manufacturing and testing electromagnetic calorimeter blocks for the sPHENIX detector. So sPHENIX will be a detector and experiment at the Relativistic Heavy Ion Collider at Brookhaven National Laboratory. The primary goal of this detector is to investigate the properties of quark-gluon plasma, which is a high-energy state of matter and kind of a fluid of quarks and gluons. So the electromagnetic calorimeter, the EMCal, is just one of several detectors in sPHENIX, and it measures the position and energy of electromagnetically interacting particles. So the EMCal is this kind of teal ring of 64 sectors. And each sector is actually made of 96 individual blocks, and UIUC is manufacturing and testing about 5,000 of these blocks and shipping them to Brookhaven. So each block is made of tungsten powder with embedded scintillating fibers, and on the exterior of this ring will be reflectors on each block, and on the interior will be the electronics, so light guides and silicon photomultipliers. So I'll explain a little bit about how the calorimeter works. So when these beams of either gold atoms or protons collide, produces many particles, and some of these particles will enter the tungsten absorber blocks, which are very dense with atoms. So various electromagnetic interactions will occur here, kind of produce a shower of electrons and photons. This shower will produce some high energy photons, which enter the scintillating fibers, where they're converted to lower energy light, visible light, and these photons reflect internally within the fiber and off of the reflector end back to the readout end, where they'll enter the light guide, and finally the silicon photomultiplier, where they'll be converted to an electrical signal. So we perform several tests on these blocks. The first that we do is just to measure the dimensions of the blocks, so measure each side length. This makes sure that the blocks can fit together in this intricate kind of sawtooth pattern for each sector. And it also makes sure that the blocks are all pointing where they should be at the interaction point in the center of the detector where the beams collide. We're also interested in the density of the blocks, since the density of the tungsten will affect the rate of electromagnetic interactions. And we want that to be consistent throughout the whole detector. The next test we perform is to test the light transmission of the block. So we have a script that actually counts all the fibers that are present in a block. And this is important because if we had a chunk of missing fibers here, then we'd be blind in that part of the detector and we wouldn't be able to see what's going on. The next test we do is to measure the scintillation of the block. So we very basically recreate the conditions of the detector and measure an electrical pulse, and we just make sure that that compares well with a calibration block, which we know is good. The last test we perform is the so-called natural light test, where basically we just take a picture of either end of the block in a natural light setting. So each of these tests gets a grade, and a block's overall grade is its worst test. So you can see this would be a C grade block here, this block would be A grade. So all of our testing data is stored in this huge spreadsheet database, where each block gets a unique identifier, DBN number, and has over 90 cells of associated information. And remember, we'll be making almost 5,000 of these blocks, so really that's an overwhelming amount of information. So when we weren't able to work in the lab due to COVID, my kind of take-home project was a JavaScript output web app, which basically allows you to put in any block number, and it'll give you all the information that we have about the block in an easy-to-read format, and it'll also dig through our Google Drive folders to find the associated testing images for that block. So to kind of wrap up the poster, the testing and quality control that we do at UIUC ensures that each block performs well, which in turn means that the crucial electromagnetic calorimeter of sPHENIX performs well, and we're able to perform these experiments, discover things we didn't know about the matter all around us.